Hey everybody, I hope you're doing well. Hey, full disclosure, it is about 5:55 on Saturday evening. It's a gorgeous evening, and I'm down in my basement making this video for two reasons. Number one, I'm taking a day trip tomorrow, which could turn into an overnight trip, and I might not be able to do this live on Monday. And I just want to get this done because I want to have a fire tonight. I want to sit outside and just enjoy. So, linear regression. It's based on Pearson's linear table, which was lesson 59. All right, so this is all what this is about. We did lesson 59 and lesson 60. So here we go. It's a relatively short lesson. Two different tests are designed to measure the understanding of a certain topic and are administered to 10 subjects. If you can't read that word, that's 10 subjects. Okay, determine whether there is a significant linear correlation at the alpha 0.05. Then this is new right here. Why is this lesson not just called linear correlation like lesson 59? It's called linear regression. For this reason. Then predict a likely score on test Y for someone receiving a score of 70 on test X. Plot the scatter diagram and the regression line. Okay, so correlation is just determining if there is a relationship and the strength of that relationship. Is it a positive correlation? Is it a negative correlation? Then linear regression goes one step further. Linear regression then makes predictions based on the correlation. So correlation comes first, regression comes second. So here's test X, here's test Y. This is the hypothesis test we did on lesson 59. Rho equals 0. There is no linear correlation between test X and test Y versus rho does not equal 0. There is a linear relationship between test X and test Y. The alpha level is 0.05. The assumptions and the test statistic are exactly the same as lesson 59. So, and by the way, you could look back in the notes. It's page 226 in Piper's notes. So I'm not going to write them here. Or Piper didn't write them there. They are omitted for brevity. So there they are. I typed this up for us. Okay. We're going to go to the skinny table for this because it's Pearson's skinny R table. Okay. We're going to reject HO if R is greater than R with 10 pairs of data at the 0.05 level. And that's look that up on your skinny table, you'll see 0.632, or if R is less than negative 0.632. To compute R, see 0.891 right there. Forget all this stuff by hand, just use your calculator. Calc, so go to stat, go to calc, do lin reg. Okay, put your X's in L1, the Y's in L2, and just for kicks and giggles, I already did that. So let's do it right now. X's are in L1, Y's are in L2. I do stat. I go to calc, then I go down to lin reg and hit enter. Make sure you do turn your diagnostic on from the last thing. All right, X is in L1, Y is in L2. So go to the last lecture, lecture 59, and make sure your diagnostic is turned on. You hit second, then 0, then go to diagnostic on, hit enter, enter again. And all this pops up. The R value is 0.891. But not only is the R value 0.891, look at the A and the B. Remember, it's Y equals AX plus B. A is the slope, B is the Y-intercept. Keep this in mind. I'm going to come back to it, actually. I'm just going to keep it right there. Okay, so 0.891, boom, there it is. 0.891 is greater than 0.632. So we reject HO, and that means we're accepting H1, that there is a significant, 4 magic words. Remember, 4 magic words: significant, positive, linear correlation or relationship between test X and Y. If this was the correlation test, we'd be done right now. Next, let's do the regression. This relationship can be expressed by the regression or least squares line given by the following formula. If you wish to compute the slope and the y-intercept by hand, please feel free to look at these formulas right here. I actually helped one of our former students who's now in college use these formulas this past semester because their college professor made them use the formulas. Okay, so there it is. And notice it says the slope turns out to be 0.51 and the y-intercept turns out to be 39.87 by hand. And I said the calculator packet gives 39.66. So 0.51 is the slope, 39.66 is the y-intercept. Let me go back to the calculator really fast. 0.51 is the slope, 39.66 is the y-intercept. This calculator gives you the equation of the regression line. How cool is that? What is the regression line, in case you have forgotten? Well, the first thing you're going to do is you're going to plot a scatter plot. You've all made scatter plots since middle school, okay? The test X scores here along the X-axis, the test Y scores on the Y-axis. Notice the breaks in the graph, okay? And you just plot them as data points. Let me scroll back up. What do I mean by data points? 75, 81. We just write that 75, 81. And then 78, 73, and so on and so forth. Okay, plot all those data points on a scatter plot. Then there is no one line that will go through any of these, all these points. You try to find the line that best averages above and below. Some points will fall above the line, some points will fall below the line. That's the point, no pun intended. Okay. By the way, it's called the least squares regression line because if you take all of the vertical distances from the line, which are called residuals, by the way, okay, you take all those residuals, the vertical distances from the line, and square those distances, all right, the line that produces the smallest sum of those squared differences, or the least squares, is the best fit line. Sounds very tedious and arduous to do if you didn't have a calculator, and it was, but now that we have the technology, it's quite simple. So the equation of this line is y prime equals 0.51x mx plus 39.66. That's the equation of that red line. Now, why is it called y prime? Because it's not necessarily an equation like we normally you draw the line and find the points that are on the line. Here we took a random scatter plot and drew a line that retrofitted a line that best fits it. It's called the best fit line. And so this line is called a best fit line, or it's called a regression line. Its technical statistical name is called the least squares, as I mentioned to you a second ago, regression line. Oh, it's also called the prediction equation. All right, it's called the prediction equation. Why? Because we're going to make predictions possibly using it. Okay, you can cancel all this stuff out. Normally, back in Algebra 1, you found 2 points, found the slope, and did all that. Don't worry about that right there. Okay, so actually, let me erase part of this. And you want to keep some of that right there. I don't know what just happened, but you want to keep this. Here we go, and this is the end. For a score of a 70 on test X, we would predict a score of, how do we get 75.36? Well, why not just go Algebra 1 style, yo? Take the X value that they give, and remember, where am I getting this from? Scroll back up. Predict the likely score on test Y for someone receiving a score of 70 on test X. So if you get a 70 on test X, what will you get on Y? Why not just take 70 and plug it in for X, which is what was done here. And you can cross this off. It's 75.36. So for a score of 70 on test X, we would predict a score of 75.36 on test Y. Done. We're finished. That's actually the end of that lecture. So to wrap things up right now, I believe I typed this up. So let's scroll down, let's scroll down, let's scroll down, let's scroll down. Here we go. Okay. Comments about the regression line, and then we're done. Sir Francis Dalton, nice dude. All right. He came up with he did some observations. He found that taller parents tend to have children who are slightly shorter than them. Shorter parents tended to have children that were slightly taller than them. It seemed as though everything seemed to be, and I'm going to go on cam for this, regressing toward an average. Regressing toward an average. And through these observations, he evolved the branch called regression analysis, branch of mathematics called regression analysis. Take many college courses on regression analysis theory behind regression dates back to the early 19th century, and this work from Dalton. Okay, it's called, and yes, so I talked the vertical distances made as small as possible. Okay, it involves calculus, tedious algebra, and it's called the line of best fit. Now, here is the most important thing. Okay, yes, words. I'm going to get right down to it. There's two options for your homework tonight when making predictions. Okay, when you perform your hypothesis test, you are either going to reject HO or you're going to fail to reject HO. If you reject HO, that means the R, the correlation coefficient, is significant. What does a scatter plot look like again when the correlation coefficient is significant? It means that the points are very tightly packed to the line, very close to the line, which means that the line is a relatively good predictor of the pattern of the points. That's the whole process of rejecting HO. When you reject HO, you say there's a relationship. The points are tightly packed to the line, so then you just plug X like we did in our lecture into the equation y prime equals mx plus b, and you make your prediction. Boom. Basically, this is exactly what we did in the notes. Problem is, what if you fail to reject HO and say there's no pattern, but you are still asked to make a prediction? Herein lies the problem. Okay, if R is not significant, that means the points are not tightly packed to this line. There really is not a good pattern or not a good enough pattern to reject HO. So what do statisticians do when they fail to reject HO, but they have to make a prediction? What they do is they take all the y-scores and they average them. They average the y-scores and they get y bar. And what they do is they use y bar as the prediction for any x value that the problem gives. So make a prediction when the score is 70. Let's just say, I'm just saying hypothetically, let's just say y bar equals 80. I'm just hypothetically, hope you're watching the video, okay? And not just looking at this afterwards. Let's just say y bar is 80 for some reason. Make a prediction when x is 70, the answer is 80. That's my prediction. Make a prediction when x is 100, my prediction is 80. You don't plug 80 into the equation. You don't do anything with 80. Y bar is just a prediction. And you might say, Claudia, that's not even a great prediction. And you're right, but there is no good prediction. So Y bar is as good a predictor as anything. Okay, everybody, that's your linear regression. Just do the homework from linear regression, not the variance and standard error of estimate, variation and standard error of estimate, just linear regression homework. Bye, everybody. I'm going to have a fire now.